Hello, and in this part we're going to be looking at how to solve circuit analysis problems in which there are Zener diodes in reverse breakdown. Now, Shockley's equation doesn't cover the case of breakdown in diodes, and there is no simple comparative formula that we can use which relates the voltage across a Zener diode to the current through the Zener diode when it's in its breakdown situation here. So we approximate the voltage against current characteristic using a series of straight lines. Now, in this module we're going to be taking possibly the easiest possible approximation, which is just two straight lines, the first one being horizontal and at zero current, and then the second one being at a fixed gradient. Now, from the definition of dynamic resistance, we can see that the gradient of this line, which is the change in current corresponding to a change in voltage, must be the inverse of the dynamic resistance. Or to put it the other way around, since we're usually given the dynamic resistance of the Zener diode that we're working with, the gradient of the graph here is 1 over the dynamic resistance. If you know the gradient of the line, then all you need is one fixed point on the line in order to uniquely characterize the behavior of the diode in this region. And the diodes will be specified as having a breakdown voltage at a particular current, and that gives you your one fixed point. For example, consider this circuit. We have a Zener diode which is rated at 5.6 volts and it's rated at 10 milliamps, which means that your fixed point on the current against voltage characteristic of this Zener diode is going to be 10 milliamps when there's 5.6 volts across the Zener. And you're told that the dynamic resistance is 50 ohms, which means that the gradient of that slope is going to be 0.02. There are now two ways to proceed to solve this circuit. The first way is to use iteration exactly as we did with forward biased diodes. We would guess what the voltage across the Zener would be. And with a Zener diode, the best guess to use would be its rated voltage, 5.6 volts. So we'll guess that the voltage at this point here is just 9 minus 5.6 volts, which would give you 3.4 volts. And therefore, the current flowing down through this resistor is just given by Ohm's law. It's 3.4 volts divided by 1K. That's my first guess here. I'll draw it out. Oh, this, by the way, is the circuit symbol for a Zener diode. I'm not sure if I've specified that before. This goes down 1K, and we're interested in the voltage across this point here and the voltage across our Zener diode. Well, if this is 5.6 volts, then the voltage across the resistor is going to be 9 minus 5.6, or 3.4 volts, and therefore the current flowing down will be 3.4 volts divided by 1K, which is 3.4 milliamps. Now, we've determined the current through our Zener diode. So this is the current that we use to get our next estimate of the voltage across the Zener diode. What we know about the Zener diode is that its dynamic resistance is 50 ohms. And the dynamic resistance is the change in voltage divided by the corresponding change in current. We know that with 5.6 volts across the Zener diode, there is 10 milliamps flowing through it. We know we've only got 3.4 milliamps flowing through this Zener diode, or at least that's our guess. So what does that predict the voltage across the Zener diode would be? This is the change in voltage from our known operating point of the Zener. This is the change in current from our known operating point of the Zener. I can work out Vz, Vz would just be 5.6 minus 50 times 10 minus 3.4 milli, which would be 6.6 milli. Okay, I can work that out. 5.6 minus 50 times 6.6 milli is 5.27. So that's my second estimate of the voltage across the Zener diode. Next, I use that second estimate to work out a better approximation of the current flowing through this circuit. If there's 5.27 volts across this Zener diode, then the current through the resistor must be 9 minus 5.27, that's the voltage at this point here, divided by 1K. And that works out to be 3.73 milliamps. So that's my next guess of the current through this Zener. Put that back into the dynamic resistance equation. 5.6 minus the voltage across the Zener, 10 milli minus my better estimate of 3.73 milliamps. Oh, that would be 10 milli minus 3.73 milli would give me 5.287 volts across my Zener, and I might decide that that is accurate enough. If I wanted to do this for another iteration step to check how accurate my result was going to be, I would just say, well, if the result is 5.287 volts, then the voltage at the top of this resistor here, that would just be 9 minus 5.287, which is 3.713 volts, and therefore the current through the resistor, 3.713 milliamps, which would give me a new, better estimate of the voltage across my Zener diode of 5.286. Hasn't changed very much, and if I only wanted the result to about 3 significant figures, that's good enough. I can stop my iteration. That's one technique for doing it. However, there is an easier way, one that doesn't require iteration at all. So the other way to do it is to note that the expression for dynamic resistance, the dynamic resistance is equal to the change in voltage divided by the change in current. Now we know one fixed point on the graph, and that is that the Zener diode is rated to have a 5.6 volt drop across it when 10 milliamps is flowing through it. So the change in voltage from that point, that's 5.6 minus Vz, where Vz is the actual voltage across the Zener, divided by the change in current from this point, 10 milli minus Iz, where Iz is the actual current through the Zener, must be equal to the dynamic resistance, because we're assuming that the dynamic resistance over the breakdown region of the Zener is a straight line. And in this case, that is equal to 50 ohms. Right. Multiply up by there, and we have 5.6 minus Vz equals 0.5 minus 50 times Iz. And that is a linear equation. There's no logarithms or squared terms in that, so we can use this quite readily in nodal analysis. All we need is one more equation which relates Iz to Vz, and we can get that from applying Ohm's law to this resistor. Ohm's law to that resistor tells me that the voltage across this resistor, which is 9 minus Vz, is going to be the current through the resistor, which is the same as the current through the diode, Iz, times the value of the resistor, 1000 in this case. So I now have two linear equations to use in two unknowns, IZ and VZ. So that's comparatively simple to solve. I just use this equation to substitute into that one. And that would give me 5.6 minus VZ equals 0.5 minus 50 times IZ. And I can get IZ from here. It's equal to 9 minus VZ over 1,000. And from here on in, it's just algebra. Multiply up by 1,000, and we get 5,600 minus 1,000 times VZ equals 500 minus 50 times 9 is 450. And 50 times minus VZ is going to give me a plus 50 times VZ. So collecting terms. Ooh, that's not 50, is it? 0.5 times 1,000 is 500. Right, 500 minus 450 is just 50. Plus 50Z, VZ, is 5,600 minus 1,000 times VZ. So that would give me 1,050 VZ on this side and 5,550 on this side. In other words, VZ is 5,550 divided by 1,050. And that gives me 5.286 volts directly. No need for any iteration because I'm dealing with linear equations. Okay, in the next talk we'll be looking at light emitting diodes.